Good morning, good afternoon, or good evening, depending on where you are in the world. Would like to present to you Lesson 16 of Basic Electronics. Would like to let you know if you haven't watched the first 15 lessons, I recommend that you do that first because this Basic Electronics course is fundamental and it is cumulative where you need to see the previous lessons to understand the present lesson. Okay? With that out of the way, I'd like to talk about what the topic of this current lesson today is, and that's about analog. Okay. Now the lesson builds on some of the fundamental principles of resistors, capacitors, and transistors. So if you don't know what a transistor, or if you don't know what a capacitor is, or a transistor is, I recommend that you review all three of them to make sure you have a basic understanding of what it is. Going forward, let's go into detail more about this lesson. First, what you want to do when it comes to analog is filter out high frequencies. You want to filter out high frequency component of a signal, for instance, to convert a pulse digital output into a smooth analog. Excuse me, a pul. Excuse me. You want to convert a pulse digital output into a smooth analog output using a low pass filter. In this circumstance, a simple RC filter will suffice to remove any of the unwanted high bandwidth PWM carriers. So your RC refers to resistance and capacitor. Okay. Now let's look at a diagram of what we're referring to here. Now what we're dealing with is we're dealing with a chip, your main board. So your main board has its voltage and current going through it through a pin through its output pin. So going through a resistor, and then you have a filtered output. The rest of it goes to a capacitor, and then it goes to ground. Also note from the actual main board there is a pin going to ground directly. If you want to have an accurate calculation of what this would look like, you would calculate the gain. So the gain is 20 logarithmic, okay, times voltage out divided by voltage in. A gain of 0 decibels, that's dB, means the output is exactly the same amplitude as the input. A gain of plus 6 decibels means a doubling. Oops, I didn't have the space here. Let's put this here. That is a doubling. Where is it? Where did I have this here? Okay, sorry. A gain of 6 decimal means a doubling of the amplitude, and a minus 6, so your plus 6 decibels means a doubling of the amplitude, and a minus 6 decibels is attenuation of the signal by half. So when we talk about low pass filtering of an Arduino generated PWM signal, what we need to consider is the RC filters. Let me give you an introduction of what that is, okay? So this was something extra I have here, but the RC filters, if this is not too small, sorry, I got this too small, but okay, we'll get it better now. Here we go. In electronic circuits composed of resistor, which is R, and capacitor, which is C, which I told you earlier, connected in a series, which means one after the other. They are primarily used to filter out specific frequencies from an electric signal. This filtering achieved in exploring the capacitor's property of storing and releasing electrical charge over time. Let's talk about some RC filters. And I think this was too small, so I'll make this a little bigger for you to see. And let's put that at 16. Here we go. Okay. So what we have is we have a low pass filter. These are types of RC filters. This is resistance and capacitor filters. It passes low frequency signals when attenuating high frequency signals. The cutoff frequency determined by the values of R and C, and use an audio circuit to remove high frequency noise. As in terms of a high pass filter, what we have is it passes high frequency signals while attenuating low frequency signals. The cutoff frequency determined by the values of R and C, just like before, and use an audio circuit to remove low frequency noise or to create a treble boost effect that has to do with the pitch of the sound. Now here is how the RC filters work. First of all, we need to consider the capacitor's impedance. Now the impedance of a capacitor varies with the frequency. At low frequencies it has a high impedance, acting like an open circuit. At high frequency it has a low impedance, like a short circuit. So basically it's the lower the frequency, the less of the resistance, and the higher the impedance, the greater the resistance. Now in terms of signal filtering, we have low pass and high pass, like I was talking about. In terms of how it works, talked about the capacitor's impedance, but for signal filtering for the low pass, at low frequency the capacitor has a high impedance, so most of the input signal voltage appears across the resistor. At high frequencies, capacitor has low impedance, so most of the input signal voltage appears across the capacitor, resulting in attenuation. In addition to that, for a high pass instead of a low pass, so a high pass in contrast is that at low frequencies the capacitor has a high impedance, so most of the input signal voltage appears across the capacitor, resulting in attenuation. That is, at high frequencies the capacitor has low impedance, so most of the input signal voltage appears across the resistor. So let's talk about some applications of RC filters. So our first application is what's called an audio circuit, which I talked about a moment ago. This is to shape the frequency response of amplifiers, equalizers, and other audio components. In terms of power supplies, is to filter out high frequency noise from the output voltage. In terms of a communication system, it's to filter out unwanted noise and interference. And then in terms of signal processing, is to extract specific frequency components from a signal. So that's your basic RC filters in a nutshell. Now, when we talk about the kind of RC filters, we would call them the first order filter, and only really works well if the signal is being filtered much greater than the frequency they want to keep. So here we have a line graph where we have the gain compared to the frequency. So the gain is anywhere from 0 all the way up to 1, and the frequency is all the way from 0, which is frequency divided by 8, divided by 4, divided by 2, divided by 0. They have double the frequency and 4 times the frequency. We notice when we start off with the greatest gain and compared to a greater frequency, we notice that the more the frequency, the less of the gain in between the two. Less of the curve actually decreases gain over frequency. That is a low pass filter's frequency response. Okay, I'll just do that better there. Okay, now gain of 1 means the signal is unchanged and is in magnitude, so it's basically at the same. 1 is at the same rate of 1. In the stop band where the signal is, so basically 1 means the signal is unchanged in magnitude. In the stop band, as I have it in quotes here, where the signal is attenuated, the signal's amplitude halves every time the frequency doubles. Okay, why? Because it requires the greater the frequency, the more power output. That's one of the reasons. Okay. Okay. Now the start and the stop band is taken to be after the corner frequency, that's denoted as the F subscript C, which I'll show you later. That's called the corner frequency. And I think I should have put an FC, but it's okay. Which is defined as the frequency at which a signal amplitude has been reduced to 75% of its original value. The corner frequency is given by this formula, which is F, as I said before, F subscript C equals 1 divided by 2 times pi times resistance times capacitance. So when you use a resistor of 270 ohms, unfortunately that didn't go over, and 300 nanofarads, which so one is the strength of the of the resistance. The second one is the strength of a capacitance. So one refers to resistor's power. Second one refers to the capacitor's power. So one is the ability to, when we talk about the resistor's power, we're talking about the ability to limit the flow of electrons through. So basically, you're limiting the flow of the current itself, expressed over voltage of the And then the second one would be an expression of how much a capacitor can store for a charge. So using a resistor of 270 ohms and 330 nanofarads capacitor, the corner frequency is, for example, this is one example. You just depends on what the numbers are specifically, but I'm just give one example. So you remember our we're going to plug in our formula here, which is F of C, that's corner frequency, equals 1 divided by 2 pi times R times C. So in this case, it's 1 over 2 pi times 270 times 330 n. And this is going to equal to 1.786 kilohertz. Okay. So that will give you an idea. The main thing is to understand this original formula, and then you can plug that in. Now, when you talk about creating an oscillator, you want to make a simple oscillator using a pair of transistors, flash LEDs, or generate an audio signal. When you use a transistor in arrangement, this arrangement also is called as astable. Astable. So if something is astable, it's not the same as. It's not the usual stable. Meaning it has no, or means no, literally no stable state. Let me just highlight that. Bold it. Instead of oscillate, so in this case, if it's astable, it's not. It's a no. It's not a, or not a stable state, or no stable state, and instead oscillates between two states. And in front of you, you see actual diagram of that. So what we're having is we have 5 to 9 volts coming in, and notice we have we have 4 resistors. Resistor 1 has 1K, referring to 1,000 nanofarads. And then we have the next one is 1 million, this would be 1K ohms. The next one would be 1 mega ohms. Resistor 2, resistor 3 would be 1 mega ohms. Resistor 4 would be 1,000 ohms. Okay, now between resistor 1 and 2, we have capacitor 1. This is 1 microfarad. Okay, between resistor 3 and 4, we have the second capacitor, which is 1 microfarad. Now, when we look at resistor 2, we go to, so resistor 2 goes to the second switch as an on-off switch. I don't mean in switch as in computing, I mean as in literally in electronics, a switch on-off switch. So resistor 2 is going to the second switch, and resistor 3 is going to the first switch. Now, the second switch is going to go directly to the ground. The first switch is going to go through current, so it doesn't what's called leak, and it's going to go through the diode, so the current is redirected to ground. Okay, so that's what this is. If you didn't see from before, this is a symbol for diode which redirects the current, or basically directs the current. Now what we have here is maybe I should put this up here, sorry. We have a 2 transistor oscillator. Now, a faster charging capacitor will win the race to turn on the transistor whose base is connected to And current flows through the transistor, turning on the LED and drops the collector voltage, allowing the slower capacitor to start charging until the opposite transistor turns on, and so on. So it's kind of like, in the meantime, you do this till this condition's met, then you go to the next condition. The frequency of the oscillator is determined by the time constant of C1, which is your first capacitor, or capacitor 1, and resistor 2, and that is relating to capacitor 1, capacitor 2 should have the same value, as should resistor 2 and resistor 3. So these should be the same. Why? Because the amount of voltage going in should be the same for resistor 2 and resistor 3. And also whatever stored should be the same as what's passed through the resistor. Okay. But it also depends on the characteristics of the transistor, okay? But we're just speaking in general terms now. When you supply voltage, for example, you could supply voltage, I just want to capitalize that. Supply voltage of 9 volts. The frequency was measured as 2.8 hertz. This was 2.8 frequencies, oscillating frequencies, implying that the frequency is related to R2, which is resistance 2, and capacitor 1 by the formula of F, which is referred to the frequency, which is 1 over 0.36 times resistor 2 times capacitor 1. Because it's sort of like, this part is this is this part, and the other one is this part, and then you put it all together and you get that. But for this one in particular, that's what that frequency is. Now, when we consider flash LEDs in series, you want to make an odd number, 3 or more, of LEDs to flash in series without a microcontroller or digital IC. We talked about that last lesson. What you want to do is you want to build a ring oscillator from something. This is a type of transistor called, the acronym is MOSFET. Okay, something we talked about previously, but go ahead and review that if you don't remember that. So moving on, what we have is an actual ring oscillator diagram. Notice we've got 3 LEDs that are lit up with this. We have the LEDs in parallel, and we have the diodes in parallel. What we're having initially is voltage and current going through the circuit. Okay, so one end is going, so it's initially going through the circuit, going through the diode. That voltage on for each one is powering the LEDs, and then at this point it's going through a resistor, and we can see the resistor 470R refers to the resistance, or the power of the resistor. And at the end of this series we have an endpoint. Now that endpoint is directed so each resistor is directed to each switch. So we have resistance 3 that's going to switch, to switch 3. Resistor 2 is going to switch 2, and the resistor 1 is going to switch 1. Now, when we deal with the next resistors in parallel, which is 4, 5, and 6, what we're doing is we're looking, so these next 3 switches will be on or off, okay? So if it's off, it goes out. If it's in, it's going to go through the resistances 4, 5, and 6. And then at the end, we have for each resistance 4, 5, and 6, they have their own respective capacitors, which is denoted as C1, C2, and C3. And the amount of charge it can hold, which is 1 microfarad, 1 microfarad, and 1 microfarad. And this is a more complex one called a ring oscillator, which it means it's going through, it's a ring in terms of the flow of through the circuit, but it's subdivided into series for each resistor, and as it relates to the switch. So the switch is connected. This will be either out, voltage out, or if it's voltage in, it'll eventually go, will eventually be stored inside of those capacitors. Now the circuit works is the way this circuit works is to think of each transistor stage as an inverter. Remember from the first lesson, inverter is something that converts direct current or DC to alternating current, which is AC. That's a inverter. Now that is if the gate of the transistor is low, then the drain of the transistor will be pulled high by the LED and the resistor, which you saw initially in this diagram. Now the final inverter stage that feeds back to the first transistor and the cycle continues. So once you've finished the cycle, it repeats. Now to avoid drops in voltage from input to output, you need to buffer high impedance input voltage that it can be attached to significant load to output without affecting the input. Okay. Now what you want to do is you want to use a BJT arranged as emitter follower as shown. I'm going to show do I okay, I have it shown below here as shown below. In this case, the input is provided by a pot. What they call a pot. The output voltage will follow the input voltage. So naturally you have input going to output. And it says less than the base emitter voltage. Why? Because it's going through a resistor. On the face of it, this may seem pointless, as you might be asking yourself why you wouldn't just take the output from the slider of R1, which is the first resistor. See, it's 10K, which is 10,000 ohms. A reason that even a very slight load resistance on R1 will alter its output voltage. Why? It controls how much resistance and voltage it allows through the circuit. Okay, that's why they call it an impedance, because it's impeding the current flow. Okay, that's another term for resistance, is an impedance, but it's always denoted as capital R. So that would be your resistance after the voltage come in. You notice 9 volts come in, you have the node going directly into this node, which is like a major point in the circuit, and that's going directly into the going into resistance. So it's like water in a pipe, and you have something that slows down the flow, of water in a pipe, just as an analogy. So the reason that is even a slight load resistance on R1 will alter the output voltage. Why? Of course, because they're limiting the current flow going through the going through the circuit. Whereas by using a transistor, a much larger load current can be drawn. Now, what we're seeing in this diagram is, of course, voltage is coming in with your current flow, passing through the first resistor at a amount of 10,000 ohms. So this is the force that can impede the current. And of course, for R1, it goes directly to ground, and that ends the circuit from that end. From the other end of the node, so one goes directly to resistance and then ground. The other end of the node will go to the switch, which is Q1, and part of it will go out to the output if it's off, right? If it's on, it will go through what's called a resistance load, which will have its own impedance or its own ability to resist or limit the current flow. And from that load, this is the resistance load, this node at the end of the resistance will go also directly to ground. Now remember that an emitter follower like this can be used in the basis of a voltage regulator, and I'll give you an example here. Actually, I want to pull this down a little bit. I didn't want that to happen. That's okay. Move this up. Okay, here we go. We see another diagram where it's something similar, except the numbers are different. So what we have is the voltage coming in through a current, and then going into resistance 1, which has a 100 resistance force, and goes into the node that can either goes directly that stops either it's going to go to a switch to on or off, Okay, so if it's off, it goes out. That's regulated output. Excuse me, that's going out. That's regulated output. And if it's going in, it's going to go through the diode, and that will actually control the flow of the current. And at the end of that node will go directly to ground. And let's talk about the next part of these diodes that we're using. And so this is called a Zener diode, or emitter follower voltage regulator. The Zener diode will keep the base of Q1, which is the switch, at 5.6 voltage as long as the input voltage is greater than 5.6, because we got to remember it's going through a resistor, so it's gonna impede the force of the current flow and how much voltage in. Okay, so yeah, so it has to be more than 5.6 voltage. The diode, as I have here, the Zener diode acts as a voltage reference to Q1, which is the switch, whose emitter will remain at 5 volts as long as the load current does not become great enough to start drawing significant base current, and hence cause the voltage at the base to drop. Okay. Now, when we want to build a low-cost oscillator from these projects that we're doing, you can do with Arduino or Raspberry Pi. I haven't talked about any of the programming behind it because that's something separate you should be looking at. But I'm just looking at the basic electronics aspect of it. What we're going to be doing is we're going to use an IC that's it's an NE555 timer IC and the configuration. So the way it's going to work is we're going to have, it's going to be, the input going in is going to range between 4.5 to 16 volts. And then what's going to happen is it's going to go to it's going to go to resistance 2 because they have an original resistor. And it's going to go to resistor 2, to the next node, and then for each lead out here, or I guess you could call it pins, it will go to a respective part of this IC. So you have trig, reset, threshold, dish, and continue, and ground. Now, this is the oscillator that we're dealing with here. And then after R2, the node either goes into this and then goes to output, or it will go, the rest of this can be actually stored in a capacitor, and that after the capacitor, whatever's left over goes to ground. Also, the second capacitor. So with the second capacitor, you have the input voltage, basically voltage in, which can range from 4.5 to 16 volts. This will go to capacitor 2 to store 100 nanofarads. That's actually, technically it's lowercase and capital F, because farads is a measure of capacitance, or the ability to store it's the measurement of a capacitor to store electrical charge. And that from there will go to the end of its node, select the endpoint, and from one endpoint it will go all the way to the endpoint that goes to ground. You notice at the end of all the circuits there's ground because you don't want excess voltage. So if you have too much voltage, what you do is you immediately ground it. So what happens, there's no more potential because we're at the same level. As in, on both ends of the polarity, they have the same level. Okay? So you want to ground it so you don't fry whatever's going in. Frying as in you're overloading the circuit. And that is an NE555 oscillator. Now, we've got some formulas to keep in mind. Now, this is basically, when you think about it, it's pretty basic, but you gotta just kind of plug it in. So what you need to do before you look at the formula, you need to consider what's happening. So what you want to do is you need to control the duty cycle of the PWM or other purposes. It's for the simple oscillator like we were just talking about. Now the frequency is set by the voltage, the values of R2 and C1, whatever those are. So you just plug in those numbers. So whatever that is, so what you do is you take the frequency It's equal to whatever the number is, and so whatever the number is, right? 0.693 divided by the value of R2 and times C1. Thus, if you follow it logically out, you'll have frequency equals 0.69 divided by resistance 2 times capacitor 1. And then when we break it down even more, that will be equal to 0.693 divided by 10K, which is 10,000, times 10 nanofarads. And that will be equal to 693 divided by 100, okay, in terms of kilohertz, because we want to focus on the application of the signal itself. Excuse me, the frequency of the signal, which is 6.93 kilohertz. And then also we need to consider also how we can calculate R2. Now R2, what we do with resistance R2 or resistance 2, we take 0.693, which is constant. We're going to divide it by the frequency times capacitor 1. So you kind of just flip it over. It's important to remember that capacitors in particular are generally only accurate at values of plus or minus 10%. And the should be frequency. And the frequency is also somewhat dependent on the supply voltage. Okay, keep that in mind in terms of your calculations. It's just like anything else, it's not 100%, but that's what it is. Now, when you want to build a variable duty cycle oscillator, what you want to do is use that original chip that I was talking about. That's the NE555 timer IC. The IC stands for integrated circuit, otherwise known as a computer chip. That's the old term. But this is in the configuration as shown here in the diagram. So we have something very similar to what we saw before. So what we're going to have is we can have the we'll have a different level of voltage, so 4.5 to 16 instead of 14 or 15, whatever it is. That will go to capacitor 2 in terms of its ability to store a charge, which is 100 nanofarads. And then it will go all the way to the end of that to its node and then go to ground, and that ends it. That's path number 1. Path number 2 is it goes to resistor 1, then it goes all the way down to resistor 2, then goes to capacitor 1, and then ground. Keep in mind that also the resistor, when it goes to the resistor, also for the output function, it needs to have pins to connect so that current and voltage goes through these pins: VDD, TRIG, reset, thresh, dish, continuity, and then ground, which will go directly from that pin to ground where the other two are going. Now, when we mentioned all those, so if you look at these individually, you notice that each one of them will pass through resistor 2. Resistor 2 will store a charge, and anything left over will go to ground. Now, the one that goes directly to the output, which should be VDD, through the integrated circuit, and then through pin 3, because you see the numbers, that's the number of the pin corresponding to the chip's function. And then this pin will go out to output. And that is a NE555 oscillator with an adjustable duty cycle. So these are those that would refer to extra functions in this IC. Now, when we talk about frequency and duty cycle, I'm going to pull this a little bit here. We want to consider the proportion of the time in the output is high to the time that is low. And it's set by the values of C1, R1, and R2. So that would be capacitor 1, resistor 1, and resistor 2. So there's two formulas. This is time high equals 0.693 times R1 plus R2 times C1. Okay, that is time high. Okay. Now, when we look at the time that is low, that is denoted as t low as opposed to t high, that will be equal to 0.693 times resistance 2 times C1. Well, what's the difference? We don't have the first resistance. So we're missing the first resistance for low. That will make the difference between high and low is that we're missing, for low we'd be missing resistance 1. Keep in mind that the overall frequency in hertz will be the inverse or the opposite of, so instead of 1 over 2 it's 2 over 1. Or if it's 2 over 1 it's 1 over 2. It's just the opposite. It's called the inverse, as you probably know from math. So anyway, the overall frequency in hertz will be the inverse of these two times added together. Just like we had resistance 1 plus resistance 2. Well, let's look at the frequency now. Frequency equals 1 over t time high plus time low. And that will, if we break it down, will be equal to 1.44 divided by resistor 1 plus 2 times resistor 2 times capacitor 1. Notice this 2 times and not R2 or R2 1 plus R2. No, it's R1 plus 2 times R2. Okay, times the capacitor 1. So that is our formula we should consider for frequency. Now, in terms of our NE555 timer, we should note that it's an extremely flexible device. It has lots of things it can do. That is, it's kind of its features if you want to look at it that way. Now, as it relates to that, we want to look at the logical operators. So when we see a sideways triangle, we're looking at logical operators. So what we want to do is we want to look at this one, reading it from left to right, because the right is the end of the circuit, the left is the start of the circuit. What we want to do is we want to look at it logically from lowest number to highest number. Okay, so we want to look at each function. So first function is ground. Second function is trig. Third one is out. Fourth one is the reset. The the fifth is continuity. The 6 is the threshold, and the 7 is the discharge, and the 8 is the VCC. So what we're doing is we see from the first one, because we want to break this down one step at a time. We know as ground goes directly to a switch, on or off, right? So if it's on, it goes to the out. If it's off, it goes to out. If it's on, it goes to the discharge. Why? Because we have extra voltage going through the circuit. Then we look at the trigger. We have to go through what's called the logical operator. Through this logical operator, we'll go to our IC. Now, for the IC, we have R1, R, and S. These are just variables, but they can be any number of things. They do need to be variables, do need to be defined. But you notice for each major one, it has its own function. So the trig will go directly to the IC, which will go to out in terms of its current and voltage. Second one, the threshold, will go through a middle point, which will be continuity, to the logical operator. And the logical operator will go to the chip and then out. And the VCC basically is basically saying, okay, this is another one that has another functionality. So that's a basic look inside the NE555 timer IC, which is what we looked at earlier. Keep in mind that the design is centered around a reset, an RS flip-flop. That is connected at the out pin, which I showed you before, which is here. And an open collector output connected to pin dish. See, that's also out. So you logically, when you read it from left to right, you can see in which direction is the current flowing, which is used to discharge the timing capacitor. So it's just basically you have the capacitor, the timing for it. Okay, the frequency compared to the capacitance, and then the rest of it leaves the capacitor at a certain rate, and it goes to the discharge. Now, if the voltage at trig falls below any of the supply voltage, I wanted to move this up here. The lower comparator, this is called the comparator, sets, and that's, by the way, that's not a typo. The lower comparator sets the flip-flop until the voltage of THRES, that's the threshold, exceeds of the supply voltage when the flip-flop is reset. And I'm not talking about sandals. So what we want to do is we want to consider this logically, how this works. This is, see, the matter I told you these are logic, what's called logic gates. It's basically like the gate is like a door, like you go to like step A, like, okay, the door, so this is before you go to the next door into the next room. So the room is basically like the highway. And the next room is basically either going to be the main place, like where the reset part of the chip is, or if it's going to go to the next operator, which is what's its next function. Now, when we consider making a one-shot timer, you want to create a timer that at the press of a button will turn the output for a certain amount of time. When SW1 is pressed, the out becomes high and high until either SW2 is pressed to cancel the timer, or a period of time of 1.1 times R1 times C1. Remember, this is R and C. These are multiplied together, okay? Now, similar to that other diagram, I guess that wants to save. Here we go. Sorry, I didn't want to. Here we go. What we have here is another schematic diagram. And basically, this is just showing you the resistors in parallel. Now, this is actually kind of counterintuitive because you would think resistor 1 would be first, but actually resistor 1 is closer to the IC. So when you go through the voltage, right, it has two main paths. One is directly to the directed to the capacitor, right, and that capacitor will go to the end point of each resistor down to ground, all the way to ground. And the other way is that in this, whatever the range of the voltage that can go through the circuit, which is 4.5 to 16 voltage, you'll go through resistor 3, resistor 2, resistor 1. Each one has split this up, so each one has 1,000 ohms for each resistor. That will limit, it's kind of like if you think of like speed bumps or roadblocks, it slows it down. It slows down how much, or prevents how much current flow can go through the circuit in terms of its load, which is its voltage. Okay, load is synonymous with voltage. Current flow has to do with is how much the force pushing voltage through a circuit. Now what's happening is after it goes through resistor 3, 2, and 1, it's going to go through this IC for an immediate output. Okay, notice we have pin 8 going to VDD, then it's sent output, which is pin 3 going to output, similar to as before. Okay. Notice the only really difference is in terms of our design is that resistance 3 comes first before resistor 1. So it goes opposite way. Also, another thing I almost forgot to mention, we have capacitor 2, which was directly going to there. So after resistance 1, we have a charge so we have the capacitor, right, that's holding the charge. Okay. That one goes to the IC. And then also after that, you also have, after that's finished, after the next logical part from the capacitors to ground. Now, keep in mind that with resistor 3 and 2, we have switches. We have switch 1 that corresponds, so after resistor 3, after it goes through the resistance, that node will go directly to the switch, logically on or off. Obviously, if it's off, it doesn't allow any more current flow. And if it's on, it goes to the node, which will pass to the next one. Is the next one on? Yes. Notice that each resistor has their own switch. Why? To regulate whether or not the current's going to go through. So it's just like a light switch. It's either on or it's off. It's a digital idea. But if it's off, you're not going to get any current or voltage going through the circuit. That's what it is. Now, when you're using an NE555 timer on a one-shot timer, so that was, excuse me, that was your that is when you're using it any. Actually, I gotta move this up here. That is when you're using an NE555 timer as a one-shot timer. Okay, that is that specific function for it, but the actual electronics of it is similar to the other one, except it just is the resistors in parallel going opposite direction. So let's suppose you want to control the motor speed. What you want to do is you want to be able to control the speed of a motor and the turn of a knob without having to use an Arduino. Okay, so in this case, what you want to do is you want to, for the PWM frequency of around 1 kilohertz, for example, you want to use a value of R1 of 270 ohms, O for ohms, and resistor 2 has 10,000, 10K or 10,000 ohms pop. And for C1 you have 100. Notice how I have the capital F now, nanofarads. This is the ability to store a charge. Similar to the other one, we're having the voltage range is between 4.5 to 16 volts. Just like before, you have two major paths. First one is it goes to the capacitor. Then after it's finished that function, it goes directly from that function all the way to ground. For the second major path, you're going to go through resistor 1, and there's going to be two subpaths. So one subpath will be subpath, is what I meant, or it's also a pass too. But diode 1, which passes, which reduces the current flow, and now that will go through, can either go to diode 1 or diode 2. So diode 1 will go through diode resistance 2. Then from there, we'll go to capacitor 1 and then to ground. For diode, it also can go to diode 2. Now, the reason why it'll go through diode 2 is because it's going to go in through pin 6 into the IC. Okay. Notice each one of these pins has a number and is attached to a function of the IC. Notice that at the first pin of the IC, it goes from that pin all the way to ground. Now, when you go, for example, for pin 8, which is the last pin, that's going into the IC, which is your chip that you're doing all this. That's controlling the motor speed, and this will go out, right? It'll pass through, this will pass through to the motor speed, and that motor speed, so that will be the power. This will regulate the power in terms of milliamps as a maximum. That will power up your motor, and then this will go to ground. Also notice that from this, there is a diode which stops the current flow from backtracking back into the chip as to prevent excess voltage. Now, when we speak more specifically about the PWM motor control using the 555 timer, we want to note that the NE555 timer, which is this chip here, this integrated circuit here, output can drive this output. This will indicate what's put out. So one is to power the motor, and the rest of it is to ground. Okay. Now, so the power output is 200 milliamperage, which is only sufficient for a pretty small motor. Remember, this is milli, not mega. Okay. So that's 200 over 1,000. Okay. Notice that's lowercase m, that's milli, capital M is mega, which would mean a million. Okay. Now, here are some things to consider. Number one, here are some considerations to consider. Now, when you draw more current than this, it will cause the IC to overheat and eventually fail. So to drive a higher power motor, you need to use a transistor. The minimum duty cycle of the circuit depends on the ratio of R1 to R2. And R1, this refers to resistor 1, should be considerably lower than resistor 2. Why? Because each one you should be the purpose is to actually reduce the current flow. Okay. So if resistor 2 was greater than resistor 1, something would be wrong with resistor 1. Okay. The point is, after each resistor, based upon their impedance, the power of the impedance of the resistor, right, to slow down the current flow, it should actually be less each time it goes through a resistor in parallel. Okay, so that's what it is. So yes, so R1 should be lower than R2 to minimize the duty cycle. Well, the current going in R2 should be less, but the R1, if R1 has more than R2, so that's just like, okay, you don't want to put too much duty. When they say duty, means is the strain on the resistor, basically. So, but R1 cannot be 0 ohms because, of course, we need. Remember, ohms is a measurement of resistance. We need to have some measurement of we need to have some ability to resist the current flow going through the circuit. If there is no resistance, then the oscillation will stop. Okay, now the ratio of 40 to 1, I need to put a space here. 40 to 1 is sufficient to ensure the minimum duty cycle is just 3 to 4%. So basically, we want 3 to 4%. Yeah, 3 to 4%, 3 to 4%. Each time it's going through each resistor, we're reducing the current flow. Now, when you apply PWM to an analog signal, which is something else, analog signal must be between 0 and VCC, and it's applied to, by the way, VCC stands for voltage capacitor, and is applied to the continuance. This is a one of the functions of the IC. Sorry, not continuance, the control pin of the IC, sorry. Well, it does continue the function, but yeah. The clock signal should be the modulation frequency and can be provided by another NE555 timer. So it depends on how this is set up. Now this can get quite complex, so what we're having here is we want to look at it from left to right again. We want to look at each function and its own path. So we have 5 volts going in, and going just like we had it going vertical, this is horizontal. So this is going directly to capacitor 2 and then to ground. Now, if it doesn't go directly to capacitor 2, it's going to go through a resistor 1 for its clock cycle, and then it can go directly to capacitor 1. Now, for each one of those things, we have a pin, as you can see, for the trig, the reset, thresh, dish, and cont, or the control part of the chip. We have each one of those chips that's coming through for control. We have the signal going through to each chip, which does a specific thing. And then finally, the last one is it's going through would be to the VDD, which will output the voltage through pin 3, which is the output. Okay. So whatever the output is, whether it's going to ground or whether it's going to a motor or going to something else, that's the output. So it's like at the end, this is the output. After all of this, after we've gone through resistor 1 and capacitor 1, we're going to go to ground. Also, our first pin there from the IC will be going to ground. And keep in mind that the PWM of an analog signal is using that NE555 timer. I know we're going into detail, but I'm going to talk a little bit more. The NE555 is configured as a monostable whose pulse length is determined by resistor 1 and capacitor 1. Remember this is resistor 1 times capacitor 1, and the voltage at the control. Remember, the control is related to the output. So the control will push the voltage through the chip, allow the voltage to be pushed through the chip to the output pin that goes out. Okay. Now, the so the monostable fires every time the trig pin pulses in response to the modulation clock. And R1, so that would be in terms of its clock, that would be in terms of its frequency. I was going to say clock cycle, but frequency. R1 and C1 set the maximum pulse length, which should be timed to one wavelength of the cycle. This would be 1 hertz. The maximum pulse length is the timing maximum, which is equal to 1.1 times resistor 1 times C1, resistor 1 times capacitor 1, or R1 times C1. So an R1 of 470 ohms and a C1 of 100 nanofarads would give a Tmax of 1.1 times 270 times 100 nanofarads equals 29.7 microseconds, because we're looking at this in terms of time. This would allow for the full voltage range of 0 to 5 volts to be modulated at PWM. And then we have one last thing to mention, that when you make a voltage controlled oscillator, or VCO, which I probably should have put it earlier, what you want to do is you want to use that, make sure that you're using the NE555 configured at a stable, and use the control, or CONT, control pin voltage to control the switching thresholds and hence the frequency. So the frequency would be the modulation of the electrical signal. Okay, so there'll be more to say about that later, about the modulation and frequencies and those things, but as it relates to what we're using, that's what it is. Now here we see an example. Sorry, I thought we're not quite done yet. Sorry. In terms of this pin, in terms of our voltage controlled oscillator, similar setup as before. Okay, the voltage coming in, capacitor direct to capacitor ground. Resistance 1, 1 will go directly, from there can go directly to out. Other ones will be for its particular functions. And then that will go to resistor 2, capacitor 1, and then down to ground. That's for our VCO control. Now, and that is, so the VCO control would be from the control pin. And then using, that would be in terms of how this chip would be used. Now, in terms of a decibel measurement, we want to understand that decibel is not strictly speaking a unit of anything, but rather a way of expressing ratios that is suitable for properties such as sound, which is a perception by humans as a logarithmic function. That is, for a sound signal to sound a little bit louder, you might double the amplitude of the voltage. A gain expressed in terms of dB, or decibels, can either apply in terms of voltage of amplitude or to power. The power is proportional to the amplitude squared. That is, that if you want to look at a gain, you consider its logarithmic function. So that would be 20 logarithmic, so it's expressed in terms of 20, times the voltage out divided by the voltage in. So in other words, a gain of 0 decibels means that the output is exactly the same amplitude as the input. So that would be the logarithmic function. Now a gain of 6 decibels means doubling the amplitude, and minus 6 decibels is an attenuation, which is reduction in the signal of this. I literally that's what attenuation is. It's a reduction of the signal. So it's kind of being redundant here, but anyway, it's an attenuation of the signal by half. Okay, that's what attenuation does. Okay, and that will do it for our lesson. That was quite a bit. I recommend going through, looking at the circuits again. But the main thing is to understand that we're dealing with voltage out divided by voltage in times whatever the logarithmic function is, okay? And that will determine our decibels. We need to understand that we're dealing with an NE555 and our functions in terms of each, there are different functions in the pin, has to come in through our resistors, which major, the two major passes, one goes directly to capacitor 2, and then after that it goes to ground. Whatever's left over goes to ground. And the other one will go directly, one pin will go directly to the output through the control pin, go to output. The rest have their own functionalities. And from there also goes the resistors 2, now to capacitor 1, then to ground. Remember, we have two capacitors. And remember, also we have our resistors in parallel. So for what we're using it actually goes the opposite. Instead of resistor 1, 2, and 3, it goes 3, 2, and 1. Okay, remember, and then understand that there's two major paths. And then also we have switches from after the resistor. So the current comes in, we have the resistor, and then the switch either on or off. Okay, if it's obviously off, there's no resistance, there's no current voltage. If it's on state, you're going to have a current flow of voltage. Remember also that there's a logical flow for this chip, and we just talked about I'm kind of going backwards, but I'm just going to show you kind of in reverse, in terms of reverse engineering here, that we also need to remember the basic functions, okay, of the timer, how the chip actually works. Remember, we have timing high, timing low. Timing high has R1, resistor 1 plus resistor 2 times capacitor 1, versus time low doesn't have, only has R2 times C1 and also times 0.693 also. Okay, so that's the other thing. It's always, for both of them, is 0.693 times R1 plus R2 times capacitor 1 for high. For low, it's 0.693 times, not resistor 1, but resistor 2 times C1. And also remember our frequency. Frequency equals 1 over time high plus time low. We need to know whatever time high and time low is. We plug in, all we really do is we plug in whatever the numbers are. So whatever is given as a variable equivalent, that's what it is. Okay. And then also we have to understand our frequency, how resistor 2 is calculated. Resistor 2 is, in this case, whatever the number is on the top, divided by frequency times capacitor 1. Okay, we talked about low-cost oscillator, and also we talked about the basic current flow for this. We have switches, goes to output, the load, and they always go into ground. So each major way, also for both ways going to ground. Remember that the power output is for the LED, and then also that current flow is from the bigger part of that diode. So diode will, as we know from previous lessons, that will direct the current flow. So the bigger part of it lets it in, the smaller part is kind of like a one way, and that's what it is. Okay, and then finally, we just for our 2-transistor oscillator, we need to remember that frequency equals 1 over 0.36 or 0.36 times resistor 2 times capacitor 1. Remember, we're talking about capacitors here, and remember that 1 is the same in terms of a low pass filter's frequency response. If it's 1, it's the same. If it's less, it's going to be degrading. If it's more, it's actually, or sorry, 1 or less it's going to be actually increased, and if it's more than 1, it's actually going to decrease. Okay. All right. So I think actually that was from us. That's from yesterday's. And this was about our analog. Remember that this is for the purpose of using Arduino or Raspberry Pi. Now, we also mentioned that we could also use that chip to control what's going on with the oscillation. All right, so I know that was kind of a mouthful, a lot to learn, but feel free to go over the video a second time just to get the particulars about how the flow is and the flow of the circuit, some concepts, and then formulas, and then you should be all set. So I'd like to take this time to thank you for watching this video, as you could be watching any other kind of science or technology, especially as it relates to basic electronics video, so I do appreciate that. As this did provide value for you to either get a refresher or to learn basic electronics as it relates to analog, what I'd like you to do is please click like on the video. That way you'll be pushing the algorithm and more people will be able to view it and enjoy it. If you haven't already, please click the subscribe button. That way you'll have access to all the content on this channel, as I certainly do have a variety of topics on this channel that you can learn from and benefit from having the knowledge of it. And also, if you haven't already, please click the bell button. That way I'll be notified of all my future videos. So as they come out, you'll be notified accordingly, and that way you won't miss any of my new videos. So I'd like to wish you a great day wherever you are in the world. Take care, and I'll talk to you next time. Bye for now.